Okay. Hello, everyone. Thank you all for coming. Gaspard agreed to give a talk today. He's a postdoc and he's been working with us for the past year or so, a little bit more than a year, in the group of Pietro Tierno. And before that, I forgot to ask where he was, but he was in France with Eric Clement, no?
Yeah.
Yeah, right. So yeah, when you want to start, you can start.
Okay, so I start. Tell me if you see the presentation.
Yeah.
Is it okay? Okay. So I start. So hello everyone. Yes, so I'm Gaspard Junot. I'm working with Pietro Tierno in the University of Barcelona in the magnetic soft matter group. So I'm a postdoc since 1 year. And so today I will present my work, which is about dynamic of driven magnetic colloids, the influence of shape on transport from peanuts to triangle. So I think you are all familiar with the concept of colloid, which is microscopic particles that are influenced by thermal fluctuations. So these colloids are used as model system to investigate properties and state of matter, states that you can also find in the atomic level, but the huge advantage of the colloids is that they are easily accessible by optical microscopy, and also they are easily manipulated by an external field. So here I show three examples of colloids manipulated by field. In the first one, it's Janus particle, which activity is activated by light. In the second one is magnetic colloids that roll upon a surface, and in the third one, it's magnetic colloids, so they rotate, and depending on the direction of the speed of rotation, they aggregate or not. So in the following, we'll focus on the third kind of systems, so driven magnetic colloids, and basically, so those systems can be used to answer two kinds of questions. They can be used to investigate fundamental questions, for example, the out of equilibrium crystallization of 2D spheres. So the first example is, as I told you, magnetic colloids that rotates, and depending on the frequency of rotation, they aggregate in a clusters and in a perfect crystal. And in the second example, made by Elena Massanacid, you have colloids, magnetic colloids that rolls upon a surface, and depending on the velocity of propagation of this carpet, you have holes in the carpet, or at low velocity and at high velocity, you have carpet without holes, so a perfect crystal. Another question, so you can also use driven magnetic colloids to in applications. So one can think about cargo transport. In the first example, so people show that you can actually transport a non-magnetic colloids with a microrod. And so the second example is more exotic. So it's a magnetotactic bacteria. So it's a bacteria that synthesizes a magnetosome, like a magnetic needle. And so this bacteria can be oriented with a magnetic field. And the idea is to load the bacteria with drugs, and to be able to target a precise place in the human body. So now hydrodynamics at the scale of colloids is mainly at low Reynolds number. So the Reynolds number, which is the ratio between the inertia and the viscous force. And so so the equation of the hydrodynamics is just the Stokes equation. So the Navier-Stokes equation, you can simplify it in Stokes equation, where you only have the pressure, the gradient pressure term and the viscous term. And if you look at this equation, you will see that it's time reversible, meaning that to move at low Reynolds number, you have to avoid reciprocal motion. So in nature, this is, for example, is achieved by propagating waves. So here is a spermatozoa where So this spermatozoa beat a flagellum and propagate a wave along this flagellum, and this make it swim. You can also move by thanks to your shape. So for example, here you can move helices, so magnetic helices, by rotating them, and they move thanks to their chirality. And you can also move by breaking space symmetry. So here it's a sketch of a colloid that rolls on top of a surface, and due to the fact that the friction force are higher close to the surface than far from the surface, you have a different friction, and this leads to a net motion of the colloids. Another well-known behavior of magnetic colloids in suspension is the synchronous asynchronous behavior. So imagine that you have a colloid with a magnetic permanent moment m, and in water, and imagine that you have a rotating field, so a field in the x-y plane. So the colloid will rotate with the field, and it will rotate with the frequency big F. So you basically have two contributions. You have the magnetic torque and you have the viscous torque. And what happened is that at low frequency, your colloid will rotate synchronously with the field. It will just follow the field, and the frequency of rotation of the colloid will be equal to the frequency of the driving frequency F. Then at some point, the viscous torque is so important that your colloids can no longer follow the field and start to be inlaid, so start to have an asynchronous behavior, and your frequency big F starts to decrease with the driving frequency. And one can predict when the transition will occur. The transition will occur when your magnetic torque is equal to the viscous torque, and this gives you the critical frequency Fc at which the transition occurs, which is basically the magnetic moment times the amplitude of the field divided by the friction force, the friction coefficient. So to investigate, so the following experiments that I will show to you have been all made in the same setup, which is basically a microscope. And on top of the microscope, there are three coaxial coils, at the center of which the sample is placed. And the sample is basically composed of magnetic colloids that sediments at the liquid surface interface, and that are driven with an external magnetic field. And in the following, we will consider three types of colloid with three different shapes. Shapes of a rod, of a triangle, and then of a peanut. And the idea is to see how these different shapes can lead to different transport properties, and how we can take benefits of this different shape. So to start with, we will talk about the triangular shape. So these are magnetic triangles that are made in Germany by Joe Tabaccoli in the University of Munich. And so basically they are made of a monomer matrix with magnetic colloids embedded in it. So this mixture is poured on top of a PDMS mold, reticulated, and then the triangles are released in water. So these triangles are isosceles triangle with a long side about 6.6 micrometer and a short side about 5.8 micrometer. So first we characterize the triangles, and basically if you apply a static field in let's say the y direction, and you switch the static field then in the x direction, the triangles will follow the field and reorient, so which means that they basically have a permanent magnetic moment. And a remark is that this permanent magnetic moment is not necessarily perpendicular or parallel to the long triangle axis. We then characterize the synchronous, asynchronous behavior of those triangles. So we apply a rotating circularly polarized field in the plane XY, which is a plane the surface plane, and we looked at the frequency of rotation of the triangles as function of the driving frequency of the field. And what you see is that at low frequency, you have a linear increase of the frequency, the rotation frequency of the triangles, and then you have these asynchronous decreases of the frequency as function of the driving frequency. So in the graph, you can see two curves, and each curve corresponds to a different magnetic field amplitudes B0. And you can notice that the critical frequency depend, as we've seen, on the field amplitudes. Then we wanted to make something else with the triangles, and basically to make them swim, to make them move. And to do so, we will apply to the triangles a rotating magnetic field in the plane XZ. Then, so plus a component, a static component and transverse component along the Y direction. So basically what the field is a processing field, and depending on the amplitude and the frequency, we will see that we can observe different types of motion. So first we will, at low frequency, so at 10 Hertz, with a circularly polarized field, meaning that the component X is equal to the component Z. So what you can see is that when you don't have the transverse component, or when you have a weak contribution of the transverse static field, you have a wheel motion, so meaning that the triangles is all contained in the ZX plane, which is the plane of the circularly polarized field, and the triangle start to rotate and to move. At some point, the polarity of the circular field is reversed, and the triangles go back to its initial position. Then, if you increase the static transverse component of the field, you will go from this wheel motion to what we call the tumbling motion. So here you can see that the triangles go a bit faster, and at some point also the polarity of the field is switched, is reversed, and the triangles go back to its position. So now, if we look at the velocity of the triangle as function of the transverse component, the amplitude of the transverse static field, we see that at low amplitudes we have this wheel motion, and at when you increase further this amplitude, you have the tumbling motion, and between the two you have coexistence between these two modes. And you can notice also that you go faster in the tumbling mode than with the wheel mode. So then, if you go at higher frequency, here 60 Hertz, and if you first start with the circularly polarized field, so the X and B component are equal, you see that you have a new kind of motion, which is basically the sliding motion. So the triangle slide on top of a surface, and sometimes you see that's a tumbling event of the triangle. So to kind of stabilize the sliding mode, we realize that if we apply now not a circularly polarized field, but an elliptical one, meaning that we decrease the Z component of the field. So this means that on average, let's say that the permanent moment of the triangle will spend less time in the Z direction than in the X direction. And this prevents the triangle from tumbling and stabilize the sliding mode. So we have, if you look at the velocity as function of the amplitude of the transverse field, you have, for a circularly polarized field, at low amplitudes you have the wheel motion. At intermediate amplitude you have the tumbling and the sliding, and then at high amplitude, you have the tumbling. For an elliptical polarized field, you also have wheel motion at weak transverse field amplitude, but this time you have the sliding mode when you increase the field amplitudes. So what you can see is that also you increase the velocity when you increase the transverse field. So now what we will do is to play a bit with the field, and basically to play with the polarity of the field. So the polarity of the two fields are in red and blue. So red meaning that we will switch the direction of rotation of the field in the ZX plane, and the blue is the polarity, the direction of the transverse static field. So I play the video. So as you can see, by playing with the polarity of the field, we are able to move the triangles in the whole 2D space. And like a striking fact, or at least something could be surprising, is that the triangle's trajectory is not parallel to the x-axis, and you would expect that with a circularly polarized field in the xv direction, the triangle will be parallel to the x-axis, but it's not. And this could be due to the fact that, as I mentioned at the beginning, the permanent magnetic moment of the triangle is not necessarily aligned or perpendicular to the long axis, and makes an angle when you apply the static field. And this misalignment could be at the origin of anisotropy in friction that will induce this drift velocity. So to conclude on this first part, we have characterized the behavior of the magnetic triangles. We've seen that they show synchronous asynchronous behavior. We've seen that under a processing field, you can have 3 different modes of propulsion, and that you can move the triangles in 2D, and that this could be due to a misalignment, a positive misalignment between the magnetic permanent moment of the triangle and its long axis. So now we are working with numeration and theoretician to try to reproduce the 3 modes of locomotion in simulation, and also it could be interesting to see if it's indeed this effect of misalignment that allows the triangles to move in the 2D space. So now, in the second part, I will talk about the experiment of microrods. So experiment on microrods have already been done for example, people have looked at the velocity of the nanorod, a microrod as function of the frequency of a rotating out of plane field. So a rotating field perpendicular to the surface, and they saw an increase of the velocity as function of the driving field. And then they have also shown, another group show that you can drag and you can transport particles, non-magnetic particles. You can trap them with the microrod. So the thing is, missing the study so the range of frequency is low. I mean, there are missing information at high frequency, and we would also we would like to have more information also on the dynamics and the trajectory of the trapped particles. So to do so, we performed experiment with the nickel microrod that are made via electrodeposition. And so the microrod have a typical length of between 5 and 8 micrometer, and a magnetic moment M of the order of 10 to the minus 13 ampere per meter square. In the following, so the nanorod will be driven with an external magnetic field, and with an external magnetic field circularly polarized in the plane ZX, which is the plane perpendicular to the surface. Below the critical frequency, the motion is still synchronous. The thing is that the microrods change, it tilts and change its orientation with respect to the x direction, which is the direction of motion, to actually reduce the drag. And so you have two configurations. So at low frequency, your microrod is aligned with the B, with the field, and rotates in the ZX plane. So this is magnetically favorable, but this configuration have a high drag coefficient. And to reduce the drag coefficient, you can tilt the nanorods and make it roll perpendicular to the field direction. So these have a lower drag coefficient, but of course the misalignment with B will cost you magnetically. So you have these two configurations, but the thing is the motion in the two configuration is synchronous with the field. So to investigate and to understand the experiment, we went back to a model that have been proposed previously to explain motion motion of spheres close to surface. So basically, here the nanorod is modeled with using two spheres that are glued together with a total length L, and that are driven by the same field, a rotating out of plane magnetic field, and propel. So these two beads propel with a velocity v. We define the angle theta, which is this tilt angle. So the angle that when you look upon the nanorods or the doublets, the angle that the long axis made with the x direction, which is the direction of propulsion. So basically, when you are in the linear regime, theta is 0, and when you are far in the second regime, theta is equal to pi, meaning that your microrod is perpendicular to the x direction. So here you can derive analytically the velocity in the x direction, the mean velocity that depends on the angle theta. And you can also have an expression for this angle theta. And this angle theta basically depends on the critical frequency, which is the same critical frequency as in the synchronous asynchronous regime, which is the magnetic moment times the amplitude of the field divided by the friction coefficient. So in the following, in this figure, I present experimental results of, in the first figure, the velocity of the nanorod, and in the second one, the corresponding angle theta of the microrods for different field amplitudes. So the field amplitudes is indicated by the color, and so the experimental data are the dots, and the solid line are the experimental fit using the expression in the previous slide. So as you can see, when you increase the field amplitude, you also increase the critical frequency, and also you can see that in the second figure that at low frequency you don't have an angle theta, and at some point you start to increase the angle theta. So as you can see, we have a good agreement between the two spheres model and our experimental results. And furthermore, we can plot the critical frequency as function of the amplitude of the field, and as predicted, it's indeed FC increase linearly with the field amplitudes B. So knowing that these frequencies, so we know the magnetic moment, we know the field amplitude, and this allows us to deduce the friction coefficient of the microrods that we find to be of the order of 10 to the minus 18, which is coherent with friction that occurs at this scale. So now what we wanted to investigate is the trapping effect of the microrods, and to do so we performed experiments with microrod and silica particle of diameter 1 micron. So you will see on the video that so nanorod is propelled with this out of plane field. It traps the particle. At some point, the polarity is reversed, so the nanorods go back to its initial position. And so you can see two things. The first thing is that you can trap the particle with the nanorod, and you can transport it with the nanorods. And also, I don't know if you can see it clearly, but you also have a transverse motion of the trapped particle across the nanorod, let's say. So the particle starts to in one side of the nanorod, then cross the nanorod and end at the opposite side. So this is illustrated in the 3 snapshots here, where so basically, as I told you, you have a transverse motion, and one can study this transverse motion by looking at the relative position of this silica particle with respect to the center of mass of the nanorod. So in the first figure, you see the x relative position, x being the direction of motion of the microrod. So you see that the trapped particle oscillates as we have seen in the video. In the second figure is the y position, the y coordinate, which is the coordinate perpendicular to the direction of propagation of the microrod. And you see that indeed the particle has a net motion in that direction, and so start from one side of the microrods and end at the opposite side. And one can compute a drift or a transverse velocity that we call that like a pumping velocity. And so this pumping velocity actually depends on the frequency at which the nanorod is driven. So it increases first. So in the second figure, you see that this pumping velocity as function of the driving frequency of the field. So you see that it increases linearly, and at some point it decreases, and that the transition occurs more or less at the frequency which is the same critical frequency as the critical frequency for the velocity. So to conclude on this second part, we have seen that the nanorod exhibit the microrod exhibit two regions of velocity that are both synchronous with the field, and that above a critical frequency, the microrod changes his angle and reduce the drag to continue to be synchronous with the field. We've seen that we can explain the experimental data with a two-sphere simple model, and that we can use the nanorod to transport colloids. And you have two direction of motion of the colloids. You have so the colloid is advected with the microrod, and also has a transverse motion that we call this pumping effect. So now we are also working with theoretician and numeration to try to reproduce the experiment and this pumping effect in simulation. So now I would like to talk about it's the last part. I would like to talk the experiment I made with the peanuts particle. So these peanuts particles are hematite particles with micron size. They are basically, they have a long axis of 2.6 micrometer, and so two short axes, one of 0.5, 0.8, and another of 1.2. So they are hematite particles, and they obviously have a peanut shape. So unlike the nanorods, those particles have their so a permanent magnetic moment, but this moment is perpendicular to the long axis. So this means that the configuration which is magnetically favorable is the same coincide with the position that's with the lowest drag coefficient. So this is the difference between the peanuts and the nanorods. And so, like in the experiments with the microrods, the peanuts are driven with an out-of-plane circularly polarized magnetic field. So an out-of-plane field in the ZX plane, and the peanuts will move with the driving field with the velocity v. So if you characterize the mean velocity in the x direction as function of the frequency of the field, you see synchronous asynchronous behavior of the velocity as function of the pulsation or the frequency, and you have a critical frequency about 681 radian per second. So now, in the previous study, people have noticed that you actually have so two kinds. If you look at the interaction between two of these peanuts particle, you have two kinds of configuration. You have a configuration so at low frequency, basically, you have a configuration where the two peanuts particle swim or propel like one behind each other, and another configuration where at higher driving frequency where they propel side by side. So this kind of behavior, they call it hydrodynamic bound states, and we can understood this as follows. So if you consider that you have an attractive dipolar forces between the two dipole of the microrod, so this should, if you only have magnetic interaction, the nanorod should move one behind each other. But what you have is that you also have a flow field generated by the rotation of the nanorod, and one can estimate the force generated by this propeller, which is proportional to omega, the driving frequency. So what you have is, like, if you consider if you compare these two forces, you see that the viscous forces and so the hydrodynamics will dominate for frequency of rotation higher than a given critical frequency, which is, so here is the pulsation, which is like 55 radian per second. So we have seen what's going on with one peanut, with two, but now what's going on if you place a lot of them and if you look at the collective behavior of this kind of particle. So here is the video with a low density of particle. So you can see the bound hydrodynamic state, the particle rotate, propelled with the field. And here a video where the density is higher. So I don't know if you can notice by eyes, but in the second one, the particles seems to go much faster than in the first video. And it's indeed what we observe, or what we measure. So here in the first figure, the first figure displays the mean velocity along the x direction as function of the density of the particle. So all the experiments have been performed at the same frequency, which is below the critical frequency. So it's still in the synchronous regime, but it's like below, or it's like greater than it's in the regime where hydrodynamic bound state dominates, but lower than the critical frequency, but still synchronous, let's say. So what you can see is that you have a linear increase of the velocity with the packing fraction, with the density, sorry. And of course, the transverse velocity is always 0. You don't have net motion in the x direction. You also have when you increase the density, you also increase the velocity fluctuation. So here, the two figures show the velocity fluctuation in the x direction and in the direction of motion, and in the transverse direction, y. So you also increase the fluctuation in the density. So now, I don't know if you noticed it, but you have we talked about hydrodynamic bound state between two particles, but you can actually have hydrodynamic bound state between more than two particles, between 3, 4, 5. And if you can look at what we call the cluster size distribution, meaning that the distribution of clusters with a size n being the number of particles in the bound state. So in the figure displayed this cluster size distribution, and for different experiments, performed on different density. So the blue, when it's blue, it's low density, and when it's red, it's high density. And you can see that as you increase the density, you converge toward the red line, and you converge toward an exponential distribution. So yeah, I forgot to mention that in this plot, it's like semi-log, meaning that when you have a line, that means that you have an exponential distribution. So how can we understand it? Experiment on aggregation and clusters have already been performed experimentally. And for example, if we look at the result of what have been done by Junot and Cécile Cotin-Bison, so basically in their experiment, they consider Janus particle, and those particles aggregate and form clusters. They only, so in the figure here, you can see in blue their experimental results, and in the solid black line is the fit. And this expression of this fit, so this basically the fit is a combination between an exponential decrease and a power law, and the exponential will act as a cutoff for the power law. So you can see in the inset that which is like a log-log plot, that you first have a power law behavior, and then you have this exponential. So to derive this expression, they use what we call the monomer approximation, meaning that they consider that a cluster to grow the cluster only grows one particle by one particle, one monomer by one monomer. And also, when you to decrease in size, the cluster can only do it by losing one monomer at time. And this, so here in our distribution, we mainly see the exponential decrease, and basically the power law, we don't see it. So we mostly have the exponential behavior. And this could be due to the fact that, for example, if we look at the cluster dynamics, so here in the video, you can see the formation of a bound state of size 3. So basically here you have a single monomer, and then a second one aggregate, and later a third one complete the cluster. So here the monomer approximation works, so you aggregate one by one. But if you look at the cluster fission, you see that first you have a cluster of size 4, and then you have one particle that breaks the clusters, and the cluster break in basically one dimer and two monomers. So clearly the monomer approximation does not work for for the fission, and this somehow would mean that you aggregate, you can break the clusters easier than you can form it, and this could be due to this could be at the origin of the exponential distribution. So to conclude, we have seen that we have seen a speed up effect, so an increase of the velocity with the density of this particle, and this increase in density is due to hydrodynamic bound state between the particle and hydrodynamic interaction. And we've seen that the cluster size of this hydrodynamic bound state is essentially exponentially distributed. So now we are working with again with theoreticians to see if we can predict and have an analytical expression of the velocity, and see if we can predict this speed up effect. And we would like also to understand the distribution of size of these clusters, and see if for example we can explain it by saying that indeed the fission events are the monomeric approximation does not hold for the fission event, or see, for example, if the 1D structure of the cluster plays a role. So with this, I thank you for your attention, and if you have any question or suggestion, I will be happy to answer you. Thank you.
Thank you very much, Gaspard. I think Ido has a question.
Yes, thank you, Antonio. Thank you, Gaspard, for the talk. Just on the latest story with the peanuts.
Yeah.
You've shown, like, quite interestingly, that the velocity increases with the density of these guys.
Yeah.
And you also investigated the cluster size distribution. So what is the connection between velocity and cluster size? You can probably quantify how the velocity is different for the different cluster sizes.
So yeah, that's a good question. You mean if you have a correlation between the size of the cluster and the velocity?
Yeah.
So this is an ongoing work. So I'm still working on it. I thought also to investigate this. Yeah, it's an interesting. I don't have the answer. My intuitive answer would be I don't know. I don't think the cluster you go faster when you are in the cluster, but you go faster when you
have more neighbors.
Yeah. So for example, if you look at the fission or the aggregation, you seem to go faster when you will aggregate, or when you break a cluster. Mm-hmm. So I would say this.
Okay. Just to continue, with regard to the exponential distribution for the cluster sizes, mm-hmm. I guess that it only applies to some intermediate regime of density, right? Because if you are very, very dense, you will not see this kind of distribution. And when you're very, very not dense, very dilute, you will not see this as well.
So clearly, if you are in a dilute regime, you won't see clusters. You will only see monomer. If you increase further the density, well, here it seems that at some point you converge toward, but yeah, maybe if you increase further the density, you will reach a power law behavior. But okay, the results seems to saturate at some point.
Yeah. Okay.
Okay, so I think Pietro has a question.
More just a commentary, Gaspard, regarding the magnitude of the rotational friction coefficient that you get from the nanorod stuff.
Yeah.
This is comparable to the one that basically was with the anisotropic doublets in the paper. I was looking at the manuscript, and there was 8.6 10 minus 19. How much did you get?
I think I get 10 to the minus 18.
18. Okay, so one order. This could be because being a rod.
Where is it?
So you get it higher friction, higher rotational friction coefficient. Maybe if you go further, when you do the feed, okay, 2.3, 18, and this was 8.6, 90. Okay, it's not so different, but you get a bit higher friction coefficient. That's well, probably because in the original paper you have a large sphere and a small one. Here you have two large spheres. Or could interpret somehow.
Yeah.
Okay.
When you compute, because you can compute the friction coefficient of a rod, also by I think slender body theory.
Yeah.
And you end up with the same order of magnitude. So I have I think I have a factor 2 or 4.
But slender body theory is for rotation around a middle plane, right? Or is also this kind of complex precessional motion?
So I think the slender body theory gives you the rotational coefficient of an elongated object, and when rotating in the plane. I mean,
okay,
without processing field.
If it's of the same order, it's fine. It's another check that this is right, because in the fitting, basically you place also the magnitude of the moment m. Right?
Yeah.
Okay. What you vary is zeta. Perfect. Thanks.
Yeah. You're welcome.
Are there any more questions? Well, if not, I do have a question, or a couple maybe. So when you have this triangle that is traveling through the screen, can you show that video for a moment?
This one?
I think so, yeah. Yeah, so here, so I understand that, this bouncing is given because you're changing the polarity of the field, no?
Yeah.
But what changes when you have the vertical bouncing?
What you mean by vertical bouncing?
So right now, you see, no, you have.
So basically, when you switch the polarity of the components, that the rotating component, meaning the component of the field in the zx plane, you switch from right to left. And when you switch the polarity of the static field, meaning the field along the y direction, you switch from up to down.
Yeah, I saw now the little signs here. And another thing was, so before that, in the triangles as well, you had this kind of synchronous, asynchronous, or this Adler type diagram, but you have a curvature. Although I think it's just one point, but do you think this point is real, or do you think it's an artifact, like an error in the experiments?
So where
so this the red curve in the experimental points, it's like a lot smoother than it should be.
Yeah.
But it's only one point.
Yeah.
All of the others are very well fitted. But I don't know if it's if you think this is real.
This I don't know. When you are close to the transition, you can have like fluctuation, and you can go from how to say, you are more sensitive to noise close to the transition, so you can.
I know. No, yeah, but for example, most of the other curves you showed, including the one that is blue, you have a very well defined peak here.
Yeah.
So this is why I was kind of curious about this one.
Okay, I can look at it more carefully, but like that I can have.
I think Sergi has a question as well.
Yes, I have a question about the wheel motion. Do you expect that? I mean, do you always expect that independently to the initial state, it oscillates inside the XZ plane?
So in the wheel motion, I would expect, with the video, that the triangles oscillate in the ZX plane. Yeah, so, I mean, with this shape contained in the ZX plane, and it rotates. It's rotating also, I think.
Okay.
In the video, it's also rotating, but it rotates asynchronously because the frequency is higher than the critical frequency.
I mean, because intuitively, I would say that in the triangle has a permanent moment, and I mean, it tends to point towards the magnetic field.
Yeah.
So depending on the initial state, I would expect that the triangle can rotate also perpendicular to how it's rotating right now, because it's still pointing towards the ZX plane. You know what I mean?
But wait, the ZX plane is the plane perpendicular to the surface.
Yeah.
So if if you, I mean, the magnetic field stayed, the vector field stayed in the ZX plane. So you would expect that the magnetic moment of the triangle will do the same, no?
Yeah. Okay.
Are there any other questions? If not, thank you, Gaspard, very much for the talk.
Thank you.
And thank you, everyone, for coming. We'll see each other in a couple of weeks.
Thank you, Gaspard.
Thank you. Bye-bye.
Thank you, Gaspard.
Bye.
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 Bye.